Hello students, here's a practice exam problem set for exam 2. Let's go to the first problem. It's an inferential statistics of sample means. Here's a problem set. Please read through all the way to the end. A sample of 21 first-year night school students' age is obtained in order to estimate the mean age of the first-year night school students. The study yielded a sample mean of 24.5 years. Assume that the age of the first-year night school students is normally distributed with a standard deviation of 16.7. Now, under this assumption, we have to answer these problems. Which approximation is more appropriate in this problem, Z or T? Normal or student curve? At first glance, it looks like a T problem, a student curve problem, because we have small sample size of 21. Less than 50, way less than 100. According to some really old textbook, the threshold is 30, but still 21 is less than 30. So it looks like a T problem, not Z problem. But it turns out it's a Z problem. Actually, there are two criteria. Roughly speaking, for Z, you need either one of these two. Large sample size, typically 100 or more, or known population standard deviation, sigma. Again, roughly speaking, for T approximation, you need both of these two. Small sample size, typically, and less than 50, and unknown population standard deviation, which will be replaced by sample standard deviation. Now, which is it in this case? Here, the population standard deviation is given as 16.7. How can you tell? Well, where is it located? Is this 16.7 located with the same sentence as the sample? Let's read through. The study yielded a sample mean of 24.5 years. Let's read again. The study yielded a sample mean of 24.5 years and the standard deviation of 16.7. Was it like this? No. It reads, the study yielded a sample mean of 24.5 years. Stop. No mentioning about sample standard deviation. Now, on the other hand, let's go to the next sentence. Assume that the age of the first-year night school students is normally distributed with a standard deviation of 16.7. This is about population. We are talking about the first-year night school students assumed to be normally distributed. It would have been a bit clearer if the problem had been written like this, with a population standard deviation of 16.7. Would have been a little bit better this way, but no textbook author will write problem like this. It's too straightforward. So naturally, this information was hidden, and you're supposed to find out from the location of this information. It was tricky, wasn't it? And if you felt a little bit uneasy about this whole business, the distinction between Z or T for sample mean, I think you're going to be okay, mostly, because this problem is a relic from the previous textbook. Currently, we are using Sullivan's textbook as the main textbook, but previously I've been using Johnson and Kuby's textbook. And in the old textbook, there was entire chapter devoted upon this topic here. In Sullivan's textbook, yes, it does discuss, but only a little, and then just move on, and then just assumes T approximation and T tests for all kind of sample means. So there goes the problem, and there goes the subtlety. And if you miss that subtlety, no big deal. Even here in this exam problem set, if the student missed that, they just miss maximum 5 points and that's it. In the other part, 1.3, 1.4, 1.5, these three, no more deduction because they were already penalized in 1.1, so it's not fair to take off anymore. Okay, let's go to the next part. Estimate the 95% confidence interval of the mean age. I have two solutions here. The preferred solution is the z approximation. Now, acceptable solution here is t approximation. Because the students were already penalized here, t problem here, that's acceptable, no penalty. Okay, let's go to solution 1, preferred solution, and let's complete it. Always begin with a picture. And here's the typical process: outline, center, end, and shade. Center is pretty much straightforward, 24.5, the sample mean, and we have to find out end, x1 and x2. Shading, I use 3 color here, but if you have only 1 color, typically you shade the middle part. Sometimes keep the middle blank and then shade left and right. Okay, here's the solution. Typical method is z-score formula, end minus center over SE. Too many fractions, so let me expand the font. End minus center over SE. So x minus 24.5 over SE, standard error, 16.7 over square root of 21. The sample size here. And then the statistic of negative 1.96, where did it come about? Well, here's the z table, and 2.5%. You see, let's go back here. 95% here, so 2.5% here, 2.5% there. So I need the left-hand side shading, left-hand side shading of 2.5%, and that's supposed to be negative 1.96. Let's go and check. Where's 2.5%? Yeah, here, negative 1.96. So indeed negative 1.96. Alright, solving this equation, that's not too bad. Flip this denominator to the other side and multiply, alright. And then flip this center to the other side by changing the sign. We get this computation. And then here's the answer if you run it with your calculator. Now, how do you find the other endpoint? We just found this one. Well, use a symmetry. From the center, I took minus to get here. So from the center, plus to get to the other endpoint. And indeed, changes minus to plus, so that's it. So what do we have? 17.36 to 31.64. And here's the conclusion. Okay, that was the z approximation method. Let's use t-curve. Initial picture, well, in naked eye, you cannot see any distinction between one and the other. If you use hand-drawn picture, then absolutely no way to tell whether it's a z-curve or t-curve. Center 24.5 and then otherwise identical structure. Now for t-curve, it's going to be more convenient to find x2, this one right inside. For z-curve, this was more convenient. Let's find it. Typical method. T statistic. T is end minus center over SE. And what is the t statistic associated to this? Well, we need the degree of freedom first. N minus 1, so 21 minus 1 is 20, so degree of freedom. And then we want 2.5% here and 95% in the middle. So let's go to that t table this time. 2.5% here, so 2.5% here, and the degree of freedom is 20. So it is 2.086. Another way is to go all the way down and 95% in the middle. In this column, find 20. Degree of freedom is 20, so here 2.086. There. So let's solve it. Flip this denominator to the other side. We have it here, and then flip this one to the other side. We get all that. And run your calculation. You get 32.1. Now that's the right-hand side endpoint here. How do you get the left-hand side endpoint? From the center, instead of going plus, let's go to the left, go minus. So go minus, and you get 16.898, 17.0. Here we go. Either way, if you do it right, you're going to get full credit. As for the selection Z versus T, that was already discussed and penalized accordingly in 1.1. Now let's go to 1.3. Does the sample study yield sufficient evidence to declare the mean age of the first-year night student exceeds 20? Set up the hypothesis. Well, null hypothesis is always about mu is approximately equal to something, and that something is never from the sample. This is no. So you have to go the other one. Always compare with 20. And then exceed 20, okay, that's my alternative. Clear enough? Okay, let's go to the testing. Let's test this hypothesis with alpha of 0.05. Okay, here's the initial picture. Center, 20, the null, and then end. Well, that is the critical value we are looking for. Once this is found, then I can compare that with sample mean of 24.5. If 24.5 falls here, then close to null, so null wins. 24.5 goes over there, then too far from the null, so null loses, reject null. That's the main idea. So let's look for this. Find out what x is. Okay, here we go. Z-score is n minus n2 over SE, and then Z-score associated to 5% is 1.645. Is that it? Yeah, Z-table. And 5% right here, 0.0505 versus 0.0595, so negative 1.64 versus negative 1.65, so negative 1.645, but this one is to the right, so positive 1.645. So that's how we got Z statistic. Flip this one over to the other side, we get that, and then eventually we have 26. That is my critical value. So we have 26 here. So compare that with 24.5. Where does it fall? Here we go. 24.5 falls in the null region. It's close enough to null that null hypothesis wins. We have to accept a null hypothesis. So this critical value is a threshold. Too far away, then null loses, so we reject null. So the final conclusion part is really easy to understand once you get the critical value. And that's why I emphasize a critical value approach. Finding this one out, not too difficult. This is something we had been doing basically for the confidence bound and confidence intervals and so on. Same kind of idea, and compare that with the picture, then we have pretty much straightforward way. The other methods require some deeper mathematical understanding, and if you know what you're doing, great, but otherwise maybe not.